Okay, we're still working with polynomials, and now we're going to be working with three theorems that help us find the exact, the roots of a polynomial, meaning if you have a parabola, the roots would be where it crosses the x-axis. If you have a cubic, these would be the roots. But once in a while, say you have a parabola that looks like this, notice it doesn't have any roots that cross the x-axis, so then you would have complex roots only, roots that involve the imaginary numbers. All right, so let me go ahead and delete that. All right, so three theorems. The first theorem is the fundamental theorem of algebra, and it will tell you the exact number of complex roots. All you have to do is look at the highest degree exponent of the polynomial. So 3 is the highest degree exponent of that polynomial, so the exact number of complex roots would be 3. All right, so that's the fundamental theorem of algebra. It tells us how many roots there will be. Now those roots could be complex, or they are complex, but remember, complex include real and imaginary. So the next two theorems help us focus on this. So Descartes' rule of sign helps us find the positive and negative possible real roots. It doesn't mean that the number that they find will be that, but it tells us the possibility. So this is what you do. You count the sign changes of the original function, and then you count it again after you've switched. When you replace the x's with a negative x, then count the sign changes again. So let's do this one up here. So I'll do this. There's a positive number right there, a negative, a positive, a negative. And if we count the sign changes, so from positive to negative, that's one sign change. From negative to positive, that's another sign change. Well, from positive and negative, that will be another sign change. So for the possible positive, positive real roots for this function right here, there's a possibility of 3. But remember, we've talked about this before. Just because there's a possibility of 3, there is a chance that there might be some imaginary roots in that. Remember, complex or imaginary roots are when there's a square root and there's a negative sign here. Well, when you take the square root of something, remember there's a positive and negative version. So the imaginary pieces always come in pairs. So there's a possibility of 3 positive or 1 positive, because 2 of those roots might be imaginary. All right, now when we find the possibility of negative real roots, what you're going to do, and here I'm going to erase all of this stuff, make that a little bit bigger. You're going to change all the x's to a negative x, and then so this would be 3 negative x cubed, subtract 7 negative x squared. Well, pretend there's a -1 right there. What's a negative times a negative? Yep, positive times a negative again. Well, that would be a negative in there. A negative times a positive, this sign now changes to a negative. Well, so let's move to the negative x squared. What's a negative times a negative? A positive. Well, what's a positive times a negative? Oh, look it, that negative stays the same. Here's negative x to the first. Well, a negative to the first is still a negative. A negative times a positive is a negative. And then there is no x to change this, so the constant, so this is what I need you to notice. The constant sign stayed the same. And look at right here. The even exponents stayed the same. Because when it's even, a negative times a negative was a positive, it doesn't force this to change. So what I want you to start paying attention to is just pay attention to the odd exponents and change the signs in front of. So notice, in front of here and in front of here, those signs change. And now look at what we have, negative, 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 negative. So there are 0 possibility of real roots, of negative real roots. All right, now we're going to go down to the third theorem, the rational root theorem. That's when you want to find all the possible rational roots. Remember, rational could include fractions, but it also could include, look at a 2 divided by 1 is also 2. Any rational root can include an integer because an integer can be converted to a fraction just like that. So this is the system or the steps. You take the factors of the constant. I'm going to erase all this stuff again. You take the factors of the constant and the factors of the lead coefficient. So the factors of the constant, positive and negative, go in the numerator, and the factors of the lead coefficient go in the denominator. And that's how you find your roots. So factors of, essentially that's the number 1, and you have both the positive and negative. So factors of 1 are just 1. Factors of 3 are 1 and 3. So this is what you're going to have. 1 divided by 1 is 1. But negative 1 divided by 1 is negative 1. 1 divided by 3 is 1/3. Negative 1 divided by 3 is negative 1/3. Or even if you give the negative signs down below, these are the 4 options they're going to be. And then once you get the rational root, you're always going to then use synthetic division with these roots. Now here is the cool thing. Look at, we have 4 options, but you can use the previous roots. Look at, there are no possibilities of anything negative. So we can cross off those 2 roots right there. We don't even have to try them in synthetic division because there are 0 possibilities of negative roots. So out of the infinite number of possibilities of finding the roots of this polynomial, we narrowed it down to a possibility of 3 or 1 positive real roots, 0 negative roots, and of the real roots, we've narrowed it down to these 4, and then narrowed it down even farther to those 2 because of this theorem. So these 3 theorems working together simplifies what roots we have to try to find. So the first one, I'm going to choose positive 1. So I remember in synthetic division, we had x cubed minus 7x squared plus 5x minus 1. And we bring down all the coefficients. And then here's the divisor right here. We're going to use 1. Remember synthetic division, you always bring down that lead coefficient. And then it's repeated multiplication and addition. So 1 times 3 is 3. So you had to put 3 right here. Negative 7 plus 3 is negative 4. 1 times negative 4 is negative 4. 5 plus negative 4 is 1. 1 times 1 is 1. Negative 1 plus 1 is 0. When 0 is the remainder, that means 1 is a factor. So I'm going to go ahead and put x is equal to 1. Well, and this is what we have left. We have a 3x squared minus 4x plus 1. and we have 1/3 and 1. I'm going to try 1 again. We bring down this 3. 1 times 3 is 3. -4 plus 3 is -1. 1 times -1 is -1. Add those together. So we have x is equal to 1 with the multiplicity of 2. That means that when you graph this at 1, it's either going to look like this or it's going to look like this, depending on the rest of the graph. When it's a multiplicity of 2, it forms a parabola shape right on the x-axis. And then what we had left is 3 and -1. Well, I know that what zeroes out, -1 is +1. +1/3 times 3 is +1. So x is also equal to 1/3. And now if we were to graph that, here is 1/3, here is 1, and because it's a multiplicity of 2, there's this parabola shape. And we know that it touches down here at -1 because this original function tells us that it touches the y-axis. The constant value always tells us where it touches. Boom, and then we can graph it. All right, that's it for this one.